Okay. Thank you very much for letting me talk. And I also had my good experiences with Boaz. And I will give a talk which again will go back to the use of monadic second order logic. So there are two things here. There is a theorem by Specker and Bladder, and there is a paper by Money and Stones, and there is my own work on the Specker-Bladder theorem with Fischer and Kotek. So these three things will come together. So here is a seemingly simple problem. We let be a graph G, a finite graph, and we put n of G be the number of vertices, m of G the number of edges, and k of G the number of connected components. And a graph polynomial PG with a vector of parameters is a function which associates with the graph G a polynomial in those variables, which is invariant under graph isomorphism. And we shall be concerned in this talk with computing the graph polynomial for a clique of size n for certain values of those parameters. So there are three examples which you might be familiar with. One is the independence polynomial, defined as the generating function of the number of independent sets in a graph G, and times x to the power of k, and sums over k. There is a clique polynomial which does the same thing, but it counts the number of cliques of size k in G. And there is the famous chromatic polynomial, which counts the number of colorings with x colors. So how do we compute it? We want to understand the sequence Pn of B, where n is the size of the clique of the input. And the question is, can we make any general statement about the sequence Pn? So in the case of the independence polynomial, we have that the number of independent sets in a clique Kn is 0 if k is bigger than 2, is n if k equals 1, and is 1 if k equals 0. And therefore, we can compute this polynomial easily. In the clique polynomial, it is similar. The number of cliques of size k in a clique of size n is n choose k, and hence we can again compute this polynomial. And in the case of the chromatic polynomial, we know that if n is bigger than, is bigger than the number of colors, then the polynomial is 0. We can also try to compute this sequence modulo a fixed number mu, and then we observe that for the independence polynomial, the sequence is ultimately periodic. For the clique polynomial, the sequence modulo m is also ultimately periodic, and for the chromatic polynomial, it is also ultimately periodic for a fixed modulus m. And the purpose of this talk is to see that this is the case for a very large class of graph polynomials subject to a definability conditions in monadic second order logic. Now, we will do this for the Tat polynomial. The Tat polynomial is a two-variable graph polynomial defined like this, x minus 1 to the k, there is a misprint here, there should be y minus 1 also. Where the exponents depends on the number of components of a subset and the number of vertices. And it turns out that even computing the Tat polynomial for a clique is not easy at all. So Gessel in 79 and independently Pak in 93 proved that the Tat polynomial for a clique of size n in parameters a, b can be described by this awkward expression, and we really don't know how this looks like. I mean, even if you have this formula, you don't know really how this behaves. So what can we say about this function for fixed a and b? And what can we say for this function for fixed a, b modulo a fixed number mu? Now, why is this at all interesting? Well, if we look at the Tott polynomial, it is known that certain evaluations have a combinatorial meaning, and in the special case where the graph is a clique of size n, the Tott polynomial at 2, 1 counts the number of forests on n vertices. The Tott polynomial on 1, 1 counts the number of trees on n vertices. And the Tott polynomial on 1, 2 counts the number of connected graphs on n vertices. Now, if we define tkn1b, and this function is called Cn of b, then this function has been thoroughly analyzed in a paper by Money and Stones in 2016. The modulus is chosen to be p prime to the power k. I'm not giving their result because it's rather awkward, but after they look at their result, they think they have a guess how the result should look in general for the Tott polynomial, and indeed they conjecture that the following is true. So they introduce phi of m be the Euler-Totient function, which is defined as the number of integers a between 1 and m, such that the GCD of a and m equals 1. So let p be an odd prime and let k be a positive integer. Then they conjecture that if n is bigger than p to the k, and ab are integers and b is different from 1 modulo p, then they can say something about this function. And if n is bigger than pk and b equals 1 modulo p, then they can say something else. Now, again, they involved the Totient function, and the proof is rather involved. And they even quote my paper with Fisher and Kotek, but it is obvious that they quoted, but they didn't read it, because otherwise they would have seen that actually something like this can be stated in a much simpler way. So the result I'm going to present here is that if a, b, and mu are positive integers with a, b bigger than 1, and GCD of a minus 1 and mu equals 1, and GCD of b minus 1 mu equals 1, then the sequence is ultimately periodic modulo mu. And the second theorem, if p is any graph polynomial, which is somehow defined using monadic second order logic, I'll come back to this, then for every mu and every AB in Z, the sequence PKNAB is ultimately periodic modulo mu. So how can one prove such a statement? Well, we will use a couple of ingredients. We will use the definability in monadic second order logic. We will use also definability in the extension of monadic second order logic with modular counting quantifiers added. And we will use the Spectral-Bladder theorem, which gives a sufficient condition on when certain definable density functions are ultimately periodic if considered modulo mu. Now, we assume that our audience is familiar with monadic second order logic, and first we will explain the Spectral-Bladder theorem. The Spectral-Bladder theorem was proven in 1980 and is probably the first and the most non-trivial application of monadic second order logic to combinatorics. And it was widely overlooked because Specker and Bladder published it 3 times in very awkward places. And finally, they published it in a book where there is a very famous paper by Moshe Vardi. There is even a more famous paper by Yuri Gurevich. There is a famous paper by Ambos Spies, and there is a Specker theorem, but somehow people didn't notice what is going on there. So what is the Spectral-Bladder theorem? For a graph on n vertices labeled, uh, we will look at, so how many graphs are there labeled? There are 2 to the n choose too many graphs with n vertices. And for a property P, denote by Pn the graphs with n vertices in P, and by dp of n the number of graphs which are in P and are and have this underlying set. So dp of n is called the density function. If P, the property, is hereditary, the density function is also called the speed of P, since it is ultimately monotone increasing function. The speed is a terminology introduced by Bolobash. And so the question is, what can we say in general about dp of n? Now, the Spectral-Bladder theorem makes an amazing statement. Let P be a graph property which is monadic second order definable, and let dPn be its density function. Then dPn satisfies a modular recurrence relation for each m, and this remains true with several binary edge relations and unary predicates on the vertices. And Eldar Fischer in 2003 produced a counterexample which shows that you have to restrict yourself to binary relations. For ternary relations, the problem is open. And for quaternary relation, Fischer gave an example which is first order definable class and doesn't satisfy modular recurrence relation. Now, if you want to do it in general, not only for graphs, then we can turn structure A with relations R into a graph called the Geishman graph. And we say that AB is an edge in the Geishman graph if there exists a relation R among the relations of the structure, such that the tuple R is in R and that both A and B appear in this tuple A bar, possibly with other members of A as well. And for any element A, the degree of A is the number of elements in the Geishman graph, the degree of the Geishman graphs. And we say a structure is of bounded degree if every element in the structure has a degree most d. And we say that A is connected if the Geishman graph is connected. And for a class of P, we say that it is of bounded degree if all its structures are of bounded degree d, respective connected. And then we can look at the Spectral-Bladder theorem again. Let P be a property of tau structures, which is MSOL definable, and let dP its density function. And now we don't have a restriction on binary relations. And if P is of bounded degree, the function satisfies a modular, the density function satisfies a modular recurrence relation for every m. And furthermore, if additionally all the models in P are connected, the function dp satisfies the trivial recurrence relation for every m, meaning that it is modulo m, it is always 0 or constant. We have no restrictions on t besides not allowing function symbols. Theorem 3 here and 5 remain true if we extend monadic second order logic to allow modular counting quantifiers. Now, to give you, I have a long lecture which is also posted, which I gave for Specker's 100th birthday. But here is some application which is maybe surprising. The following density functions satisfy modular recurrence relations because P is monadic second order definable or modular CMSOL definable. If P is the class of connected graphs, if P is the class of 3 regular graphs, or if P is the class of Eulerian graphs. And in the case of 3 regular graphs, Redfield in 1927 and rediscovered later by Polya and his students, computed, and I haven't verified this, I must say, I cannot, I don't know, but it's in Palmer's in Harari's book. Then the density function for 2n is given by this crazy expression. And obviously you don't see that this expression is ultimately periodic modulo any modulus m. So this just is to illustrate that the Spectral-Bladder theorem is a very, very strong statement. Now, let's go back. Oh shit, just a moment, please. Sorry, I'm back. So now we want to prove the string for the Tate polynomial, and we rewrite the Tate polynomial by taking the sum of the coefficients out, and then we interpret f(a)(b) of n is the function which is the remainder here in the given by this, and we look at the MSOL definable density function for f(a)(b), which is given by the structures with unary predicates u, r, and s, which says the following. Phi1 says that the u's form a partition. Phi2 says that the r's partition and each is A closed. And Phi3 says that the S is also a partition. Now, all this can be said in monadic second order logic. So it follows that FABN is ultimately periodic modulo every mu. And once we have done this, we prove a lemma. Let D1 and D2 be two integer functions. Assume that C times D1 of n is ultimately periodic and GCD C mu is 1. Then D1 is also ultimately periodic modulo mu. And the second lemma says that let T mu be positive integers with GCD T mu equals 1, and assume that T to the n times D2 of n is ultimately periodic modulo mu, then D1 is ultimately periodic modulo mu. And then putting all this together, I skip this now, then we get no, first we have to prove this, sorry. And then we put this together, and to complete the proof, we take D1 to be the Tate polynomial we want to compute, and D2 to be B minus 1 of the Tate polynomial we want to compute. And then we have our FABN can be given as A minus 1 to the n times D2n, and this is ultimately periodic for the condition we have here. And by lemma 6, we have that D2 is ultimately periodic modulo mu for GCD of this condition. And by the lemma 6 before, we have that D1 is ultimately periodic. Hence, we have proven the theorem. Now, so this is the first theorem we prove, which gives a simpler version of the periodicity than stated by Money and Stones. Now, if you want to generalize this to a large class of graph polynomials, we look at the case of graph definable polynomial where A ranges over subsets of vertices of a graph G, and phi be a formula, and then we look at the polynomial which is defined as sum over all subsets of V, such that the graph with edges G and A, and we sum over this, and the independence polynomial and the clique polynomial can be written in this form. So if it is graph definable, then we have edges, and if we want to have it over edge relations, then this is like a hypergraph, then we can do the same. So there are many graph polynomials which are definable in this way, not all of them. And if you do this more generally, then we see that the chromatic polynomial is not definable in this way. but it is definable with an auxiliary order relation, provided the definition is order invariant. The general definition proceeds inductively and also and allows also multivariate polynomials in a fixed number of indeterminates. I wrote a big chapter about this, but for the Tat polynomial, you really need a bit more general uh, framework. Now, the Spectral-Blatter theorem can be applied in the case where an order is used, even in an invariant way. So cannot be applied in the case where the order is used, even in invariant way. So theorem 2 is not a generalization of theorem 1. Now, to prove theorem 2, which says that for anything which is hypergraph definable, we can do the same thing. We prove it for hypergraph definable polynomials given by a formula psi, and we want to analyze the graph polynomial for the clique of n elements for this polynomial here. And again, we look at the density function of a relation like this, where phi1 says that this is a partition, and then we again can apply the Spectral-Blatter theorem, and therefore we get our result. Now, the conclusion is we studied properties of the sequence P for a clique with various graph polynomials, and what is so special about the clique? Well, one thing in the case of the Tat polynomial is special because you have a combinatorial interpretation for some of the values, but in general we can ask, why do we do this for cliques and not for other graphs? So yes, we could take the complement, uh, but however, if there is a but in general, it doesn't seem to work even if the graph property is such that for every n there is up to isomorphism only one graph. So there is only one clique of size n, there is only one empty graph of size n, there is also only one cycle of size n, or one path of size n, or one ladder of size n, and so on. So it would be actually a natural question whether you can make a similar statement for cases like this, but it seems beyond our reach at the moment, and it remains an open problem. Well, I think I have reached my time, so thank you for your attention.